Well, good evening, everybody. Hey, you want to come over for just a second? You mind standing right here? I want to introduce you to these people. This is the video camera. So everybody, I'd like you to meet Alex and Casablanca Painting. You might have some new customers. So you're just finishing up?
Yeah,
How many days were you working here?
about almost 2 weeks.
2 weeks.
2 weeks, yeah, and but it was a pleasure to work for you guys. You know, give us a chance, and we're glad to do some painting.
It was a pleasure having you. I'd love to shake your hand, but I don't think I'm supposed to.
I know.
Yeah. But I'll spread the word, and I'll let these guys know. Based out of Yakima, but you're happy to travel.
Yeah, I have most of my customers here in
Okay.
Ellensburg. So
Okay.
yeah,
Well,
I see you.
thank you very much.
All right.
I feel like I know you now,
All
Alex.
right, thank you.
All right, we'll see you. Okay. So, if you're in Central Washington and looking for some excellent painting, interior and exterior, but they just finished up. They just loaded up the truck and away they go. And Liz is thrilled. And if Liz is thrilled, then I'm thrilled. A pleasant good evening to you all. Welcome to Ellensburg, Washington, USA. This is the local time, and we will begin our program at 6 p.m. here in just a few minutes, a little bit more than 10 minutes from now. Our topic tonight, Sedimentary and Metamorphic Rocks. It's still Rock Week, but this is the last of 3 of our Rock Week lectures. This was Tuesday night mineral identification. It's on YouTube. You can find it if you're interested. Igneous rock identification. That was last night. So that's part 1 and part 2. We'll use some of those skills tonight, but much of tonight kind of stands alone. And tonight we'll talk about sedimentary and metamorphic rocks in just a few minutes. Tomorrow's Friday. I won't see you. Saturday morning, gulp. I'm talking about the Milankovitch Cycles. I've started to think about it. I've started to read a little bit. I have a few ideas, but I got a ways to go, and I may run out of time, but I'll put something together. Milankovitch Cycles on Saturday morning. A look back at Mount St. Helens 40 years ago this weekend on Sunday morning at 9 a.m. How are we doing? We have some threatening skies behind you, but I think we're going to hold off. We might have a little bit of wind noise, but we're going to use that back camera again. 5x5, excellent, good to see that. Hello, 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 hello. Hello. Hola. Still watching Nora Lee quite a bit. Hola. As she jets around South America. On Wisconsin, bro. A couple of thank yous. So a very bulky package arrived this morning from Owens Meats. There's 2 old school meat operations in Cle Elum, about 30 minutes away. Owens Meats and Carrick Meats. But this was sent to me from Owens Meats. Lots of stuff from Brogan in Seattle, AKA Bubble Boy. So if you're interested in some excellent pepperoni sticks, I've got plenty. Thank you, Brogan. 2 huge packs of this amazing beef jerky. It's the good stuff. I mean, this is expensive stuff, Brogan, so thank you. So let's show a little piece of beef jerky from Owens Meats unwrapped. I'm a fan, but I'm too cheap to buy it most of the time, so this is a treat. Thank you. All right. Beef jerky. God, that's good stuff. I don't know, is beef jerky a thing around the world? Do you call it something else besides beef jerky? I'm so grateful for those two family-run operations that have been doing things for a long time. This episode of Nick from Home brought to you by Owen's Meats. You gotta love it. And one other thank you. 2 boxes arrived from Australia half an hour ago. So here's one of the boxes. Fragile. All sorts of packing and bubble wrap, and you get through all of that and you're like, what in the world is so fragile? Well, you got to be able to read it. Let me fill it up. See you guys. Let me fill it up from some wine from White Heron Cellars, a gift of John and Nancy last week or more. So this wine glass is from Kathy in Australia. She wanted to make sure I had a proper wine glass Nick from Home. Pairs nicely with beef jerky. But wait, there's more. There's another glass from Kathy. This time we'll use the Don from Gard Vinters here in Ellensburg, a gift of Tony and Greg that I thanked last night. So here's an even bigger Nick from Home. We got to fill it up. You got to be able to see the full effect. Oh, Lordy. Not quite. Thank you, Kathy. Very appreciative. I have proper wine glasses now. Salute. Delightful. Wine corks from the Whidbey Island couple. Can't remember your name at the moment, sorry. So it might get a little blowy, as Jack Zentner used to say, windy in other words. Oh, we got bijou. And so I want to make sure these wine glasses don't tip over, so give me a second. Hi. You want to say hi to these guys? If you're new to us, you know, we're screwing around, but it's mainly just to kind of make sure we're functioning properly. We've got 3 minutes. I'm double-fisted. How we doing? Save the wine, says John. Hi, Bijou. It's going to be Nick on the floor. Hi, Ryan and Jack, age 13 and 15. Good to see you. I can't say I'm heartbroken that we've got clouds covering the sun temporarily. I guess because that oak shadow we had last night. I guess now that I say that, we might not have quite the pop that we had. I was very pleased with the focus on the back of the camera last night. And it's good we had that last night for igneous rocks. Tonight, sedimentary metamorphic rocks. I don't know if it's as crucial. Thank you, Mark, for the feedback. Video and sound, great. Okay, I got 2 minutes. Would you mind giving me a second to think about what the game plan is, and we will begin shortly. Did you want to say hi? You can say hi. These guys want to say hi to you. These guys wanted to say hi to you. Yeah, right up here. Look at there. Look at there. Oh, yeah. Oh, do you see what's going on? You want to say hi? What are we going to talk about tonight? Yeah, what do you think of the paint job? The guys are gone. Alex and his brothers, and Alex and his sons are gone, so you can relax now. There's no more loud noises and strange people, right? Okay. All right. You say goodbye. Goodbye. I know. Okay. Oh, it's the jerky. I get it. You want the jerky, huh? Hey, how's it going? Well, good evening from Ellensburg, Washington. My name is Nick Zentner. I am a geologist. I like to study sedimentary and metamorphic rocks. This is a backyard session that is very casual and spontaneous and full of fun. Won't you join me in my backyard to see all of these marvelous samples that has been created? I hope that you enjoy our session. I've always wanted to do that. Okay, thank you for joining us. Let's go ahead and get started and get right to it. We're talking about rocks tonight yet again. This is the third of our 3 sessions on rock identification. Our first night, we actually had to look carefully at minerals. And on Tuesday night, we were preoccupied with things like this. Beautiful quartz crystals. Beautiful quartz crystals that have these 6-sided crystals that come to a point. You can see that there's a whole cluster here. And our point was, we can only get minerals that form these crystal faces if there's room. Yes, these minerals grow, and if they have the space to grow, they can blossom into these wonderful crystals. That's not the topic tonight. Last night, we realized that minerals, most of the time in Mother Nature, looks like this, where we actually have rocks. This one has been sawed with a rock saw so it can stand firmly on a bench. But this is a piece of granodiorite from Mount Stewart. It's 93 million years old. Hola! This is from Mexico. and was sent almost 2,000 miles north. That's a story for another live stream that we've already had, by the way. But our message is igneous rocks, our topic last night, were rocks that all had one thing in common. I don't care what kind of igneous rock it is, and I'm not going to parade them in front of you again because we did it all last night. But all of those igneous rocks, from pumice to rhyolite, from welded tuff down to basalt to gabbro to obsidian, they all had one thing in common. They were igneous, and that means that they used to be molten, and that molten material, that magma, lost its temperature. We had hot liquid magma that cooled off and solidified and became an actual rock, composed of different minerals. Another major message from last night is that if you have an igneous rock and it was cooled magma once upon a time, in other words, it used to be hot magma that's now cooled off, you're going to have minerals that are randomly arranged. Shut up! The robin. These are individual minerals that don't have any rhyme or reason. That's not the story tonight. And in fact, let me flip you around. Oh, this is a heavy rock. Hang on. Again, with an igneous rock, can you see that we have kind of interlocking crystals here? It's almost like this is a jigsaw puzzle. And we have jigsaw puzzle pieces that fit together. You're looking at an example of an igneous rock. Fresh minerals, meaning that they sparkle when there's bright sunshine. Heat is involved. And the basic message of an igneous rock, fresh, sparkly minerals that are randomly arranged. The light's different tonight, but I actually think it's kind of good. So let's try another one. You don't have to do the cult-like repeat like we did last night. Same idea here. Igneous rock, fresh minerals that reflect light, sparkly minerals, in other words, that are randomly arranged. You got it. Well, we do have other kinds of rocks on the planet. We have two other categories. We're leaving igneous, and we're going to sedimentary and metamorphic. Are there some basic rules we can use for those two rocks, like we had with igneous? The answer is yes. First message. Sedimentary rocks are composed of fragments. And that's a general term, but I want us to remember that tonight. Pieces, little fragments of previously existing rocks. Now you can have super obvious fragments like this. This is a sedimentary rock, and you're like, oh, what kind? What kind of sedimentary rock? Well, that's coming. But this has fragments that have been glued together. You know, they're not falling through my fingertips. They've been cemented together by Mother Nature. You want to see another sedimentary rock without naming it yet? I'm like, well, that's a dud. Well, it's a dud only because you are not able to see very easily the fragments that make up this sedimentary rock, but they're there. If we get down to the microscopic level, we could actually see individual fragments. So whether we have super big, gorgeous fragments or microscopic fragments, that is the common denominator for all sedimentary rocks. And yes, one of our goals tonight is make a list of sedimentary rock names. You probably know some names right now, but we're not there quite yet. Okay, cemented fragments. While we're on this kind of grand order of things, let's finish out the thinking. Cooled magma, fresh random minerals, cemented fragments indicating that we've got broken pieces of other rocks that existed in other mountain ranges and other river systems, and those fragments have somehow been brought together. They've been swept together and have been glued together to form a sedimentary rock. What's the third category? Metamorphic. Now, from grade school, you remember the basic message, don't you? All metamorphic rocks are rocks that have been exposed to extremely high temperatures and or extremely high pressures. And the result is taking a rock and changing it. You know that the root of metamorphic, that word, is to metamorphose, to change, to physically transform an innocent rock that's not metamorphic, physically transform it into a brand new rock with new minerals and a new texture, and having it be called a metamorphic rock. So all these guys have that in common. All these metamorphic rocks have that former life, essentially. But you can see how I've drawn this. Here are the individual fragments. I happen to draw them as circles here, but they're not always circles, as you just saw. But with metamorphic rocks, you can see that quite commonly, not always, but quite commonly, the minerals are actually arranged. The minerals are not random, the minerals are lined up. And it's dangerous to use the word layers, because we often think of the Grand Canyon as having layers, and that word layers is on the scale of looking across this amazing canyon and seeing rock layers from a distance. Those are actually sedimentary rocks at that scale of layers. But if you are using the word layers at a very small scale, like a hand sample scale, that's what we call it in geology. If you have a rock that's the size of your hand, it's a hand sample. And so here's an example of a metamorphic rock. You can see if the sun was burning bright right now, you'd see a bunch of sparkles like we had last night. In other words, fresh minerals, high temperature minerals. But you can see, I think, you want the zoom version? You can start, if you get close enough, you can see individual minerals, but obviously they have been lined up. They have been organized. And that's a classic look of a metamorphic rock. So before we quit tonight, we're going to learn before we quit tonight, we're going to learn sedimentary rock names. We're going to learn different metamorphic rock names. But we got to make sure before we quit, we comment on the former life of each metamorphic rock. Because I'm saying that if you're a metamorphic rock, you used to be something else. And then got exposed to all these temperatures and pressures to completely transform into a new scene. So if you're into buzzwords, like we had plenty of buzzwords last night, one buzzword tonight is protolith. Protolith, all one word. Protolith is the former rock before it was metamorphosed. Oh, I have a metamorphic rock X. Well, it used to be Y. The Y is the protolith before it got heated up and pressurized. And in the olden days, when I first started teaching 30 years ago, I'd use an analogy of a pressure cooker. I think I even lugged in a pressure cooker from my mom's kitchen once. When I was visiting over the weekend, I grabbed her pressure cooker. Well, people don't know what pressure cookers are anymore, but I have fond memories of my mom making jams and jellies and other things, both my parents actually, using a pressure cooker. You know what that is? Big kettle, you put on the stove top, you clamp down the lid, you crank it down a little hard, you turn on the temperature, you increase the temperature, but there's no escape, and so you're pressurizing things inside of the pressure cooker as well. Basically, if we take one of these rocks, put it into the pressure cooker, do its thing, take the lid off. After all that high temperature and pressure, you're left with a metamorphic rock. And yes, you can have a metamorphic rock. Put it in the pressure cooker, jack up the temperature and pressure, create a different metamorphic rock. It makes no never mind. We good? Okay, I think that's the end of my introductory comments. We feeling okay? It's time to drill down now to some detail. Yeah, we're going to lose that sun the rest of tonight. Interesting. I think I want to reposition the back of the camera as I like that green backdrop, courtesy of Sculpting and Alex. Oh, you want to see the notch that's all repaired now? Does that look nice? I don't know if you could hear Alex, but he's a very pleasant guy. Okay, So you're going to get dizzy again. I thought that worked pretty well last night, so I'm going to do it again. I'm going to do some talking to you. I'm going to flip you around. I'm going to use the rear camera to zoom in on some details, and we'll just go back that way, okay? That's the last time that area will look semi-clean. Okay, so to get into the details, and I'm going to kind of do sedimentary and metamorphic rocks at the same time. That seems kind of weird, but you'll see why right now. Here's one whiteboard for us tonight, and I want you to see what I've drawn. It's a mountain range on the left, and it's the Great Plains on the right. This could be the state of Colorado if you want. The Front Range and a bunch of rivers coming out of the mountains and flowing out onto the Great Plains. The concept we want is that rivers are not just moving bodies of water, they're carrying sediment. They're carrying rocks of all sizes. And these rivers, and it's not just Colorado, it's rivers around the world, have a magical ability to sort out their rocks by size. If you carefully study a river system, you can see that different piles of rocks are dropped at different stretches in the river, and there's a general decrease in the sediment size. What are these? Well, these are fragments. These are rock fragments, man. So I'm talking about the makings of some sedimentary rocks right now. The mountains is the source of the rock, but we're going to drop these different piles. If you're trying to get a sense of things, think of these as river cobbles, like round river stones, like in a cobblestone street in Europe, for instance. Let's have these be smaller than that. Let's have these be smaller than that. I don't know. This is like, what is this? Oh, let's have this be sand, and this is silt, and this is clay. Okay, so cobbles, sand, silt, and clay. So let's not get hung up on this. This is not a lecture on rivers, but basically we have the rivers doing this because the river is losing its velocity. It's losing its speed in general as it crosses eastern Nebraska and western, whatever. It goes for a couple of states worth of transport, and we're losing our energy, we're losing our speed, and so we're dropping certain sizes of rocks at certain spots. The point for us tonight is that river is going to keep dropping sediment every day of every month of every year of every century of every millennia, and we're just going to keep loading sand right here. And if the river keeps dumping sand and keeps dumping cobbles and keeps dumping silt, we're going to bury the stuff that was there before, and we're going to continue to bury this stuff. And eventually, these grains of sand, which would fall through my fingers if I picked them up in the riverbed — you've been to like a sandy place in a river. Eventually, we're going to bury those sand grains to a magical depth between 1 and 3 kilometers depth. That's a totally phony set of numbers, but I've used it for years. I don't even remember where I got it to begin with. There's plenty of exceptions, blah, blah, blah. But we take loose sediment, we get that loose sand and get it down to between 1 and 3 kilometers, and we create a sandstone, which is a sedimentary rock. RX is an abbreviation for rocks. Isn't that clever? Not my abbreviation. We use it all the time. Okay, so there's enough temperature and pressure. Think of the weight of a kilometer worth of loose sand sitting on top of you. That's a lot of weight. And think of the pressure as well. If you swum to the bottom of the deep end of a swimming pool, your ears start to hurt. There's a lot of pressure there. So the temperature and pressure is going to convert our sediment into sandstone. Let's do the same thing here. Cobbles, bury it. We're going to create — I'll write out the names for you in a second. Conglomerate sedimentary rock. Silt stone. Shale. Okay, so these rocks tell stories. If you have a general concept of a particular scene that a sedimentary rock represents, oftentimes you can visualize some sort of river system long ago. And if you're a desert now, or if you're in a place that doesn't have any mountains and doesn't have any deserts, but you see all these rocks of a certain age, you can reconstruct in your mind, in your scientific paper, some sort of ancient scene where we had mountains and rivers and everything else. But as you can see, I'm going to do more with this whiteboard before it goes away. we're going to continue burying the sediment on the bottom of the river of different sizes of sediment. And that means the conglomerate, the sandstone, the silt stone, and the shale are not going to stay in the 1 to 3 kilometer window. Is that true? We have audio problems? Let me just pause for a second. I just happened to see a couple of comments talking about sound. Is that a problem? Are we okay? Yes or no? Sounds fine? Slight issues? Had troubles? Really? Loud and clear. Sounds good. Nothing major. Some minor issues. Muffler boy. I wonder what the problem is. Let me move just a touch closer to the window. Liz is exercising using some streaming upstairs, but that's not been a problem before. I noticed YouTube was down this afternoon for just a little bit. It's kind of surprised me. Okay, out of sync, really. I don't know what the problem is. Okay, we're going. So I don't think I'll write everything out, but we can take a sandstone and bury it greater than 3 kilometers, have higher temperatures and pressures, and no longer can we remain a sandstone because we've been in the pressure cooker. And we end up with something called a quartzite, a metamorphic rock called a quartzite. Or we can take that shale and add some temperature and pressure and become a slate. So this is a conceptual idea of how we can get some clastic sedimentary rocks and their corresponding metamorphic equivalents by simply burying things underneath a river system. I'm certainly not saying all sedimentary and all metamorphic rocks are created in this way, but this is an example of how you can kind of have some visuals in your head, which is kind of what I normally do out here, but this is Rock Week. And I know the rules with Rock Week. We just want to see some cool looking samples and we want their names, man. Cut the story time, bro. Okay. So here's our scorecard tonight. I was yelling just in case there were sound problems. Not really. So here are some of our actual rock names that I want to show you tonight. I have examples of each of these. I got a parking ticket on campus, by the way, today. I load the van up. The campus is closed. It's 7:30 in the morning. I go early so the parking Nazi doesn't find me. I load the van up next to the geology building for 10 minutes. Guy's doing his job. All right, I get it. But the conversation was something like, first of all, do you know who I am? And he's like, yeah, you're that oversized clown. I'm like, oh, okay, you do know who I am. And then I said, the campus is closed. Why do I have to buy a loading permit? I'm teaching from home. Anyway, $35 later, we're good. Okay, great. So here's our scene. I got all these samples from school. $2 per sample. I got plenty of money. Please don't send me money. Please don't send me money. All right, so sedimentary metamorphic. This is our general rule that will get us through these guys, and then I've got some kind of wild cards that I want to show you as well, okay? So if we look at our sedimentary rock, I'm going to start in just a second. If we look at our sedimentary rock, we have our cemented fragments. Are those fragments greater than grains of sand? We all know what a grain of sand is. We've all been to the beach, hopefully, at some point in our life. Okay, sandcastle time, grain of sand. Are the fragments bigger than grains of sand? Are they sand-sized, or are they tinier than sand grains? Okay, so let's even ignore the metamorphic. Let's just knock out these 6 guys right here. Sound like a deal? Let me grab 2 sedimentary rocks that both have fragments that are bigger than sand-sized grains. You've already seen one of them a couple of times. Goodbye. Look at that paint job. here is a sedimentary rock with some stones that have actually fallen out. No, I'm not gay, but it's none of your business if I was or not. Would you please go elsewhere? So you can see these river rocks, that's our interpretation, are rounded. There's actually more of them that have fallen out that have stayed in. But that's bigger than a grain of sand, isn't it? So this is a conglomerate. This is a collection of rounded river rocks that was high up in our stream system where the energy was high, but obviously these have been glued together. Oh, some geologist in the past has helped us. What does it say? Oh, that checks out. Good, that makes me feel good. Great. As opposed to what? As opposed to this guy I've shown you a few times. Obviously, these are not rounded, are they? This is third grade now, but each of these fragments are bigger than a grain of sand, and they are angular. So, of course, there's a story for this as well. Do you have an idea? The conglomerate was obviously a river story. In other words, a conglomerate is formed in a riverbed where there's high energy water. What do you think is the story here? Must be an interesting story. Well, one common way to create breccia, that's what this is. It's an Italian word, B-R-E-C-C-I-A. This is natural. It's not tar. Breccias form in fault zones. So if you have a major earthquake and you shatter the crust at shallow levels, this is one way to find a fault zone by mapping out where the breccia is. The breccia is most heavily brecciated. You can use it as a verb right next to the fault itself. Okay? Breccia and conglomerate. I'll keep flipping back and forth. And I got to pick up the pace. We're 6:25 already. So conglomerate and breccia, greater than sand-sized particles. And let's not lose sight of the fact that we could tell tremendous stories with each of these rock types. But again, it's not story time tonight. Let's move on. Let's look at sandstone. Actually, two different kinds of sandstones that we hammer on pretty carefully in the lab because we have both of these sandstones available in Central Washington, and there's a different story for each. But I just realized I didn't grab any arcosic. I guess I was flustered by the parking guy. So I just have some quartz sandstone to show you. I don't have any arcosic sandstone, but I can tell you the difference. Sandstones are made out of sand-sized particles. Aren't you glad you tuned in? The difference is, if you are a quartz sandstone, every grain of sand is smoky quartz. Remember smoky quartz from last night? Gray, glassy, hardness of 7, scratches glass. So a quartz sandstone is kind of a pure sandstone. Every grain of sand is the same. It's the same mineral, quartz. And therefore, it's very well cemented. I'm sure the quartz sandstone I'm about to show you is not crumbly. Quartz sandstone usually glues together very well. But the sample I don't have, sorry, is an arcosic sandstone, which is what we call a dirty sandstone, meaning that you have quartz sand, feldspar sand, hornblende sand, in other words, a bunch of different minerals that are sand-sized, but it's harder for Mother Nature to glue those different kinds of sand grains together, and therefore arcosic sandstone is quite crumbly by nature. They're both sandstones, they're both sedimentary, but it's the quartz sandstone I have to show you here. Remember, we're getting smaller now. We're getting smaller. I don't know if we can even pick out individual grains. This feels like sandpaper. You can almost feel the quartz sand grains more than not. You know what? You're important, except for that one dude. You're important. And I'm gonna break this. This has been rubbed over by so many generations of Central students that we can't even see the sand grains anymore. Give me a second, I'm gonna crack this open. Before, right between the eyes. Whoa! I wish you could have saw that. It just kind of shattered. I didn't expect that. Hang on, let me get something to scoop that up. This is pretty sweet. So these sand grains have been, this is a quartz sandstone from southern Utah. So these sand grains were glued together for the last, I don't know, 200 million years until this evening. And I didn't expect the rock to crumble like this. But I guess it makes sense. Look at that. Look at how fragile. I really didn't expect that. But every grain of sand, that's not bad, is it? Every grain of sand is the same. Smoky quartz. So you're looking at sand from a beach. A Mesozoic beach. There were dinosaurs walking around. I promised I wasn't going to do story time. So those that are all nervous and shaming me for breaking the sample, blah, 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 it's still together. There's a nice fresh surface now. Do you feel okay now? So students will have a nice fresh surface to look at as opposed to this is what I was trying to show you before. Okay? It's train time coming through the canyon. Don't you just want to jump on a train sometime and just see where it goes? Or is that just me? Not bad. Not bad at all. Let's keep the pace going. So we're working our way down this column. We're decreasing the size of the sediment as we go. Now, oh Lord, how are we going to do this? We got two sedimentary rocks that I'm sure you've heard of that are composed of fragments that are smaller than grains of sand. Hell, we had a hard time even seeing the sand. Now we're supposed to see stuff that's smaller than sand? Well, these two rocks are very, very difficult to tell apart in the field. Meaning if you're a field geologist or you're teaching a field geology class, it's a challenge to make a call between shale and limestone. Both have these teeny tiny fragments that you can't see. Both are kind of soft rocks. Both come in different shades of maroon and white and gray and all over the place. It's almost like minerals. You can't just memorize a color. So if you're out there doing some field geology and you need to make a call for your geologic report and you've got either shale or limestone on your hands, how do you tell the difference? Do you know? Well, it would help if you had a bunch of rocks that had labels on it like this, like this, but they're not labeled out in the mountains. So here's what a shale looks like. It's the clay. So you're now looking at the situation. The painter guys dropped the shale, but whatever. Great job with the painting. I just shamed them. That's on me. So we're only going to get this tiniest clay particle material to deposit if we have absolutely still water. A river going into a freshwater lake or the Mississippi flowing into the Gulf of Mexico. We need quiet water, absolutely dead calm water to have that tiniest clay particle family fall to the bottom. And the result is a shale. So it's platy. Some of you asked about rock cleavage last night, or you asked about cleavage, and I said there's something called rock cleavage. Here's some pretty decent rock cleavage. Maybe you can see that there's different Oh, sorry. Pretty good, huh? So we can see layers of clay that fell to the bottom of that quiet body of water, and it's now been lithified into a sedimentary rock. This is shale. Now, shale's kind of boring, I guess. But I'd say it's not boring if you have life that was in the swamp. So I showed you this on our plant fossils. I don't know, what lecture was that? I forget. A climate lecture, I guess. So here are some fossilized palm leaves from 56 million years ago that fell into a lake or a poorly drained swamp area, and we have record of that. Let's look at a few more plant fossils. Here's another shale. Looks different, doesn't it? Different color, but it's got tiny particles. And yep, here's a leaf with some veins. I don't know the age of this. Here's another shale, sedimentary. With the central student trying to identify it, so scratching it all up for posterity. I'm surprised they didn't scratch their name into it. Have you seen some of the shale in southwestern Utah? I'm sorry, southwestern Wyoming near Green River. Some amazingly delicate preserved. I think this one was dropped and somebody glued it together. They felt so bad. This might be Silt Stone actually, which is, it feels a little bit siltier. It feels a little bit more kitchen flowery. So there is a gradation between shale and sandstone. You can have some silt particles that represents just a slightly higher level of energy. Isn't that amazing? I don't know the exact age, but here's a leaf that fell into a body of water tens of millions of years ago, and we still have preservation. Okay, so I still haven't answered my question. How do you tell the difference between shale and limestone? Because limestone kind of looks similar to those guys. Muffler boy. In fact, this real duddy looking thing is a limestone. And you say, well, that doesn't look anything like the shale. And I agree, it doesn't quite have that cleavage that I was looking at before with you, but this is limestone. Let me show you a couple other limestones out the back. We're talking about sedimentary rocks composed of very fine particles. Now, mostly the fragments are very fine in this. This is the Kaibab Limestone from the north rim of the Grand Canyon. Obviously, is that a brachiopod? I'm not much of a fossil person. I think it is. And this is 270 million years old when we had a warm, shallow sea covering northern Arizona. But remember where we are in our discussion. We're just looking at sedimentary rocks that don't have anything inside to actually look at. I spent a week on the north rim of the canyon. I'm sure I was out of the park when I collected this. I got one more. I got the best limestone for you. My first teaching job was in southwestern Ohio at Miami University in Oxford, Ohio. And it was a pretty cruddy place for geology, except for these amazing limestones in the Cincinnati, Ohio area. Fossiliferous limestone, that's the understatement of the year. So I don't know how many field trips we did at Miami University looking at these limestones. I didn't even know anything about limestone, but of course we had to go down to Houston Woods, I think it was called, along the riverbank there, and you just pull these trilobites and other kinds of amazing Ordovician marine fossils out of this limestone from southern Ohio. I mean, you're a long day's drive from the ocean, and yet you're looking at deposits from the ocean. It was worth it, bringing those in. It looks like you liked some of those. So what is the answer? How do we tell the difference between shale and limestone? I think many of you know, don't you? In case you don't, let me show you. You might remember on Tuesday night, I was showing you the mineral calcite. And calcite has 3 cleavage planes. This is a mineral now. 3 cleavage planes at 75 degrees to each other. And there's the cleavage planes that reflect light even though we don't have sunlight. And this is the one that I said I can prove to you that it's calcite because it reacts Can I get the focus right so you can see this? I'm dropping acid left and right here. And double-fisted with wine. There we go. You can kind of see it. Oh, I got acid on my thumb now. All right, that didn't work so well. But the answer is, if you are a field geologist, you always have a little vial of HCl in your backpack. And this is the most reliable way to tell the difference between shale, which will not fizz, it will not react, it's just clay, and limestone, which will always react with hydrochloric acid. Now, I was kind of disappointed with that dropping acid on the calcite. Let me try it on one of the limestones. Which one do you want? Which one do you want me to put the acid on? Which of those limestones? I show you 4. You wash my thumb off while I do that. The acid that we use is about 15 parts water to 1 part acid. The Ohio one? All? That's a little greedy. Not on a fossil? Well, that Ohio limestone is so chock full of fossils, I'm not going to be able to miss a fossil. So all of them, you guys, you are impossible to please. I like your enthusiasm, though. All right. It's the Ohio rock. Kim wants the black one. I think I get the right angle here so you can see the bubbles. Here we go. What? We got a river of... Hang on. So it's bubbling, but it's not bubbling very well. All right. Here's the Grand Canyon one. Yeah, baby. All of them, you say, huh? Oh, we got a fizzer. We got a fizzer by Joe. Hydrochloric acid reacting with calcium carbonate in a limestone. Fun with acid. Wavy gravy. Kids, try it at home. Okay, let me see if I have any more sedimentary rocks for you. I gotta wash my hands off again. Washed them off with wine. I got some metamorphic rocks. I brought them to show you. Let's go ahead and switch gears then. One more review of our sedimentary, go over to metamorphic. So we worked our way, do you remember? We worked our way kind of down this list, and I don't think I have any extras for you. Those are the 6 main sedimentary rocks that I wanted to share with you. Feels like I'm forgetting something. Here's a silt stone. Beautiful, huh? Okay, the rest of tonight is switching gears and going over to metamorphic rocks. And you remember now we're gonna take these rocks and put them in the pressure cooker. So to remind you of that buzzword, protolith, here's how it works. Quartzite is a metamorphic rock. The protolith of quartzite is quartz sandstone. The former life of quartzite is quartz sandstone. In other words, take a quartz sandstone, add a bunch of temperature and pressure, crush the grains of sand, and you'll get quartzite. Why not? Let's do it. So this was the quartz sandstone, do you remember? Quartz sandstone. That's the one that I crushed and was surprisingly fragile. I still don't think you can see individual grains of sand, but if you use your imagination, maybe you can. Now imagine putting this in a vise, squeezing over millions of years, adding some temperature, and what is the result? A metamorphic rock called quartzite. And this is the best looking texture of a quartzite that I have for you. Can you kind of see this real dense, flaky look? I mean, it's flaky, but nothing's flaking off. I mean, it is this was a river rock. This was a full river rock of quartzite, and I just went crazy on it with a sledgehammer. It's very difficult to break open. Not today, I forget when I did it. You guys are all over with your comments, by the way. Come on, let's focus on this now. So this is amazing look of quartzite, and if you are a fan of quartzite, as I am, you always have this kind of dense, crushed sand grain look. That's really what I'm talking about. Let me show you a few other examples. You really are having trouble with audio tonight. I don't understand. I don't know what else to do, so I'm just going to keep going. I'm very disappointed if we have technical problems tonight. More of that crushed, sand grain look. This is more of a purple quartzite. Here's another one, just to drive the point home. It's YouTube's fault, not mine. Okay, well, I guess they're still having problems. That's unfortunate. I certainly hope that the replay is flawless. I'm going to be very bummed if it's not. Okay, that's enough of that. So yeah, we've got this amazing, that's a good-looking quartzite now, and I can't emphasize enough how hard this is, how difficult it is to break a quartzite open. Okay? Quartzite. Now, commonly confused with quartzite is a metamorphic rock called marble. And you know marble, like a marble statue or something like that. It's metamorphic rock, but students are usually very surprised at the look of raw marble instead of polished or marble in a monument of some sort. Now, marble used to be limestone. So you remember the limestones that we were putting a bunch of acid on. Warm, shallow sea, that's the story for a limestone. But if we take a limestone and add temperature and pressure, we're actually going to make a marble, which is a phaneritic texture. Minerals are nice and big in a marble, and there are calcite growths. So this is a kind of counterintuitive. When you heat up and pressurize a limestone, it becomes a marble rock which has bigger minerals than it did when it was a limestone. In other words, those calcites are thriving on the new temperature and pressure conditions. Cue the marble. So here's the limestone. I'll do it this way. There's the limestone. This is the one with the brachiopod in it, remember? Okay, fine grained texture, can't see anything. Now let's heat up that limestone and cue the marble. This is what raw marble looks like. And if the sun was out, we would actually see cleavage planes on these calcites. So marble, raw marble is almost like it's like a white granite in a weird way. It's dangerous to say that because this is metamorphic, but it's a beautiful raw metamorphic rock that again does not look like this oftentimes in civilization. If you got a bunch of buffering, I'm just going to ignore your comments, okay? I'm getting bummed out. I'm just going to look at your comments. Okay? They almost look like glittering diamonds, but they're not. It's a calcite. Okay. The last thing that I have planned for you is what happens when you take a shale, which is sedimentary, that's at the bottom of our lake, and then we're just going to continue to bury that shale. Let's go to that whiteboard again. So the last part I have for you is basically following what happens to our shale. Our shale is sedimentary. We're going to bury the shale to have it become slate. I'll show you some slate. We're going to bury the slate and we're going to make phyllite. We're going to bury the phyllite. We're going to make schist. We're going to bury the schist and we're going to get metamorphic gneiss. So it's almost like I should draw that out. Stream completely, and I hit reconnect, I guess. So apparently there are system problems across the platform. Okay, are we back? I'm inside sitting right next to the modem, just in case that has something to do with it. But I've been sitting here a while. Thank you. I appreciate the words of encouragement. I've done this enough now where I guess I don't immediately think it's my issue. Yeah, I'll try to, that's a good idea. I'll try to go over to data, see if that helps. Okay, I'm on data exclusively now. Yeah, I'm trying not to get mad. I just don't like it when we have fouls up like this. You know, I put a decent amount of effort into making these work, so. I'm just going to hang out here for a little bit. Good evening. We're doing okay, huh? Did that solve it? Okay. Drop the phone. Oh, God. If you're typing in a bunch of problems, I'm not looking. I can't look. I can't look at you. Am I backwards now? I'm going to finish what I had planned. Back to the board. Here we go. Shale, sedimentary rock. Do you need a reminder? Has the rock cleavage to it. It's relatively soft. I could probably break some of this, yeah. Okay, but if we add a little bit of temperature and pressure to shale, we suddenly get out of the world of sedimentary. We cross a threshold and we're into metamorphic slate. Let me try to show you a decent picture of a video clip. I'm flustered now. Thank you, Dennis. Yes, I might be drinking both bottles tonight. Okay. Got texts flying in, people trying to help me out. We got you saying there's problems. All right. I've got a slate here, hang on. Here, this is a beauty. This is a beauty. This is, it kind of pings. It's got a nice kind of high-pitched ping to it. And this is what slate looks like. It's actually almost bordering on phyllite here, but it's definitely not shale. Shale is a softer version of this. So this is basically what you do when you take some shale on the bottom of a lake and you put it into a pressure cooker and you just add the temperature and pressure just a little bit. Okay, I'm on a roll. Let's keep going. Uh-oh, now what do we got? We got something that looks kind of similar. This is a very heavy sample. But if the sun was out, muffler boy, if the sun was out, we'd actually have a bit of a sheen here. There'd be a kind of a glistening on the surface here. This is phyllite. I'll spell it for you on the chalkboard in a second. So we went from shale to slate. Now we've added a little bit more temperature and pressure, and we have phyllite. Okay? We're just increasing what's called metamorphic grade. And by increasing grade, you're increasing temperature and pressure. If you're a low-grade metamorphic rock, you're down here in the slate category. But if you're a high-grade metamorphic rock, you're increasing the temperature and pressure. And you can think of this, if you want, with our burial process, or in the guts of a mountain range. I can't hold the storytelling. As we continue that continent versus continent collision and continue to add temperature and pressure, in the guts of that mountain range, we're creating more and more high-grade metamorphic rocks. Let's keep going. What's next after phyllite? Let's add more temperature and pressure. What are we getting now? We're still metamorphic. A metamorphic rock called schist. These are essentially all foliated metamorphic rocks. There's another word for you. Foliations means the minerals are parallel to each other. It's what I have. Can you see it? It's right here. I'm showing foliation with the metamorphic rock. And all of these metamorphic rocks, slate, phyllite, schist, are foliated metamorphic rocks. I've showed you one of my most beautiful samples that I have right on my desk, and the students who are sitting there for advising and worried about their future are often distracted by such a beautiful rock sample. Can you guess? I've showed it to you probably 2 different times in the last week. Can you guess what I'm going to show you? It's a schist. It's the schist. I love this sample. It's called a Garnet Schist. These are garnet minerals. Garnet mineral. The conditions have to be just right to not only convert the phyllite into the schist. That's not the sexy part of this sample, obviously, but you can maybe see we don't have sun again, but we should have some kind of sparkly, sheeny type look. Yeah, there we go. The minerals are oftentimes full of mica. The biotite and the muscovite mica are parallel to each other. And then unimaginably, these gorgeous, I don't even understand the process, but these amazing garnets pop up. So not all schists have these amazing garnets in them. And to be honest, I can't even remember if I brought in another schist or not. But this garnet schist is, if you want to come in for advising, you can drool over this schist. And avoid eye contact with your advisor. There's one more step in the process before we go to magma. I mean, we're about to get so hot, we're almost ready to melt the whole thing. And if we melt the whole thing, we're back to where we started last night with igneous rocks, right? If we have magma, it's igneous. But we've got one more high-grade version. Hi, Bijou. I've heard all the puns. I've been around the block. Nice. Yeah. Yeah. You like metamorphic rock? So all these beautiful zebra-looking rocks, let me show you a few. I've showed you some of this already. So now we have such high temperatures and pressures, we're actually kind of segregating our minerals, black and white. We're getting the black biotites, the black hornblends to align themselves, and then we're getting the gray smoky quartzes to show up as well. These are 2 separate rocks from 2 separate locations. But it's a pretty fair look at metamorphic, high-grade, nice. I've got a very beautiful sample from the Appalachian Mountains that I did not collect. Actually, I did collect this one. This is some nice from, where was I? Central Idaho, in the Pioneer Mountains of Central Idaho. We have a geology field cap there. Oh, you deserve to see this one. I said that wrong. Of course you deserve to see it, but this rock deserves to be seen. This is another good example. Not a granite, right? Granite would be randomly arranged minerals. This ain't that. Beautiful. Gneiss from the Pioneer Mountains of central Idaho. I like this lighting better. Let me show you that other one again. Oh, it's maybe from the same location. And then the Appalachian sample I promised. So you can get these amazing folds. This has obviously been cut by a rock saw. These wonderful migmatites and other kinds of very complicated, swirly looking metamorphic rocks. It's all in that category of metamorphic gneiss. There's the raw look. So you don't have to know anything about geology to know that this is a very special sample. And maybe you've been to some places that have this kind of metamorphic rock. Well, let's see if I have anything else before, oh, it's after 7 o'clock. Some of you know about serpentinite. That's a prized local rock. It's a metamorphic rock. It's greenish. It is basically basalt that has been metamorphosed. Typically forms in a deep ocean trench. Bijou's hunting birds now, making that weird sound. I think that's all I got for you. Let me get the wine, and I'll answer some questions. Nick from home. Brought to you by Kathy in Australia. Ooh. Needed that. We're running long, but that's okay. I'm not going to see you tomorrow night, and I'm sure you have questions. I always feel badly when I see the replay and I see excellent questions that I just missed. I promised that I didn't see your question. I would not just kind of look over your question on purpose. You have my word. I don't know what your reaction is. I knew that guy hated me. He never reads my question. I don't hate you, I love you. I'm a lover, not a fighter. Scrolling back. People telling me to get the wine. Did that. Are there intermediate stages, or do these metamorphic rocks change suddenly from one to the other? Papa Dop, I don't have a good feeling for timing of this, but I know of no evidence of a very sudden metamorphic change. Even in the case where you have contact metamorphism, where you have a magma chamber that's truly just baking surrounding rock and creating metamorphic rock as a result. I think we're talking about millions of years regardless of converting these protoliths into metamorphic rocks. I don't know how to back that up, but that's my general sense, that we're talking about long geologic time frames to create these metamorphic rocks. Where's the garnet schist from? I didn't collect that. There is some garnet schist to find in outcrop form near Lake Wenatchee, but I've just seen tiny little garnets there. That's obviously museum quality or close to it. And many of the samples I'm shared with you have just kind of been handed down, you know. You teach for 30 years, you collect a bunch of stuff, you have it in the lab, and then you retire, and then you leave all the samples there. A bunch of the samples I've collected, I'll just leave for the next person. Hopefully that's not anytime soon. We're not talking about obsidian tonight. That was last night. North Columbia River Beach is full of all this stuff. Did it come down from Canada? North Columbia River Beach. Susan, if you mean the North Cascades or extreme northern Washington, that's exotic terrain country, meaning there's big blocks of metamorphic rock that were moved to Washington from other locations. And so, yes, Washington is loaded in igneous rocks, hardly any sedimentary rocks here in Washington. Did you notice I didn't have any real local examples of sedimentary rocks? And the metamorphic rocks that we do have are in the North Cascades because it's out of the German chocolate cake. How do garnets make room to grow? I wish I knew, Corey Sue. I don't know that process. It's quite interesting, isn't it, to see these incredible, perfect garnets? All I can say is that there's certain temperatures and pressures where certain minerals grow, and there are minerals that only form as metamorphic minerals. In other words, they need sky-high temperatures and pressures, and once you get into that window of temperature and pressure, if the ingredients are there, you form. But I don't have any more than that cartoonish version of it. What textural properties of marble make it so good for sculpting? Mary, I think it's just because it's soft. You know, there'd be a lot more sculptures out of granite, but granite is hard. It's made out of quartz and other hard minerals, if you remember Tuesday night's session. And calcite is a soft mineral, and therefore marble is a soft rock, and it's easier to sculpt. My grandfather was from Italy, and he was a stone cutter. So it runs in the family, I guess. But he died before I was born, so I didn't get personal accounts of the business. It's a monument, Zoya Monument Company in Woodstock, Illinois. Quartz lenses in slate, what causes them? I would think of moto mining, I would think of quartz lenses or quartz veins as the result of being in that pressure cooker. You're in a high temperature, high pressure condition, there are cracks that form, and quartz is filling those cracks like toothpaste, and lenses as well. So I wouldn't think of the quartz lenses as being, well, maybe you are thinking of the quartz lenses as being part of the metamorphic rock, but oftentimes they cross-cut the foliations in the metamorphic rock. If you're asking about quartz lenses within, no, you're asking in slate. So yes, cross-cutting. Can higher grade metamorphic rocks have the same original protolith? Can higher grade metamorphic rocks have the same original protolith? I'm not totally sure I get the question, but I can answer it this way. That beautiful gneiss that I showed you. So what's the protolith of gneiss? What's the protolith of gneiss? Schist. What's the protolith of schist? Phyllite. What's the protolith of phyllite? Slate. In other words, going backwards. But you can also have a granite, a salt and pepper granite, and add a bunch of temperature and pressure and go straight to a gneiss. So if you're asking, is it possible to have more than one protolith for a certain metamorphic rock that's high grade, the answer is yes. Oh, look what I found over by the rocks. What's the green metamorphic rocks on Tip Top Mountain? I'm sorry, Gail, I don't know where that is. If it's in central Washington, it's probably serpentinite. Was the last green rock serpentinite? Yes, Lindsay. We have a lot of beautiful green serpentinite, which is kind of slippery like snake skin. That's why it's called serpentinite, like a serpent skin. And this has a deep ocean story, and we have much of it in the foothills of Mount Stewart, just to the north of Ellensburg. But many mountains, Mount Shuckson, etc., are made out of that serpentinite, metamorphic rock, metamorphosed basalt. Garnets, Lake Wenatchee. Does marble react to hydrochloric acid like limestone, asked Bob. And Bob, I'm sorry I missed your question last night. Sometimes the marble does react, and you're right that marble used to be limestone, and limestone reacts with acid, so wouldn't the marble? I don't know, do you want to try with the marble? Oftentimes the metamorphism changes the rock so much that it loses its ability to fizz. Well, we got the marble here and we got some acid. Let's do it. Let's get away from my laptop. We don't need an acid spill. This might be much ado about nothing, but let's try it. Crud. I can't get you to see without tipping it like that. I tried. No, I'm sorry, it doesn't. But I have seen some raw marble that does. I think maybe if I whacked on that marble and got some fresh surfaces, it would react, but I don't want to break that marble up. Especially with all the sensitive souls here who don't like me breaking anything. The jumping scroll routine never gets old. Actually, yes, it does. How long does it take to feel confident in identifying? S. Merck, thanks for the question. I'm 57 years old and I'm still weak on identifying things. So I think some just naturally take to it and they go in that area. I mean, they don't become a public speaker. They're kind of detail-oriented and wanting to learn a bunch of detailed terms, and it's just not my thing. So I'm always weak in identifying, and especially if somebody comes in off the street, it's always awkward because they already kind of know the answer according to themselves. They just want confirmation. And oftentimes I'm sure I know that they have something different than what they're saying, and then it gets uncomfortable in a hurry. What does granite metamorphose to? Matthew, I would say nice is a nice... Nice is one of the options. Probably the easiest option for us right now. Why does serpentinite sometimes have a fiber-like texture? Blue Forest Roads in Japan. Do you have serpentinite in Japan? Because it is a deep ocean trench rock, so maybe you do have some serpentinite. Why does it have a fiber-like texture? Well, our serpentinite here doesn't have that. There are some high-temperature metamorphic minerals that are fibrous. I can barely remember even their names, like andalusite and kyanite, and I don't think those are in serpentinites, but there might be a, serpentine is the mineral, and maybe you're seeing some of the individual serpentine crystals that are fibrous. A gneiss implies movement as a plastic rock? Yeah, you can think of it that way, Will. Those foliations are oftentimes parallel to each other, perpendicular to a stress direction. But those beautiful folds that I showed you, that's a plastic scene. That's a ductile kind of a interesting set of conditions that I'm not sure I totally understand. Please tell me about epidote, says Kim. Well, epidote is kind of a pistachio green. It's usually found in association with garnet. I mentioned casually contact metamorphism, but I used to teach a field class for 20 years down in the Owens Valley of California. Every September, I'd bring 25 Central kids down there, and we had a field mapping exercise along the east front of the Sierras, just to the west of Bishop, California. And there was a skarn deposit, S-K-A-R-N, and that's a collection of minerals that thrive in those hot fluids along the boundary between the Sierra Nevada batholith magma and the surrounding limestone, which has now become marble. It's a place we used to call Marble Mountain. And so there were beautiful garnets, and then these epidote crystals were this kind of pistachio green that were beautiful. I don't know much more about epidote than that. But that was something. How strong is the HCl? About 14 parts water to 1 part acid. I mix up the HCl solutions for our department, and I'm always careful not to make it stronger than that because it does eat through people's clothes, even with that dilution. How did the Appalachian gneiss form, says Joni? Well, you get metamorphic gneiss quite often in the guts of a continent versus continent plate tectonic collision. And Joni, are you holding on to something so that you don't faint? If you haven't heard this, the Appalachian Mountains formed when Africa collided with North America, when the supercontinent Pangaea was put together. And Africa is no longer next to North Carolina because Africa backed away from us, or we backed away from Africa, or both. But that beautiful metamorphic gneiss is not only beautiful, but it's telling a story of Africa colliding with us. I love geology so much. And I guess you do too. Can you find fossils in marble? Probably not, Lynn. I don't think I've ever seen a fossil in marble. You're right that fossiliferous limestone is a thing, but I think that temperature and especially that pressure is going to destroy those fossils. There's no fossils in any metamorphic rocks that I can think of. Is gneiss always layered like your samples? Yeah. Not folded like this. I showed you some of the gneiss that just had the black and white foliations, but it's usually banded like that, like zebra stripes. Justin Simpson, what will the rock from craters of the moon become after going through metamorphic processes? Fell for it! Serpentinite's the answer. We'll do a few more. What the heck? I'm back to feeling okay, and I guess we don't have... I didn't hate somebody's question, DT. Professor drops too much acid during class. I've heard them all, by the way. Hey, Nick, you rock. Let's see what you did there. Nobody's ever said that to me. Good job. What's my main area of research at the moment? I don't do any research, Zach. I stopped at a master's degree. I did not go on and get a PhD. I found my calling in life was to communicate geology to non-science groups. And I continue to do that. So my points of emphasis do not fit easily in an academic world, but I continue to see a great need for it, and I enjoy it very much. A few more and we'll quit. Did slate really get used as chalkboards in the olden days? Kelly, let me tell you about the olden days. Back when I was young, we didn't have computers. We had classrooms with maps that you pulled down like a window shade, and you had chalk and you had actual slate. And we liked it. This is fun. Where does sugar stone fit in? I don't know about sugar stone, Melanie. My only guess is that that's marble. It has a sugary texture. Broad jam though 57757. Let me take another drink. This is good wine, by the way. Tony and Greg, thank you. What is the material in between the river cobbles holding it together, and how did it get there? Yeah, I don't know. You're asking about this conglomerate, and there's glue holding this together. Quite often you get some clay that's even calcareous, meaning that it fizzes. So in other words, you get some sediment mixed in with the river cobbles and then the whole thing gets buried and turns to stone. You can even get a meta-conglomerate where you keep burying that conglomerate and then it becomes extra solid. Is anybody still with us, by the way? 825, is that true? Let me refresh. 741. Still pretty good. I guess you're still interested. Fred, I'm sensitive to noise. We don't hear it. That's true. My wife has trained me to become extremely sensitive to noise. Thank you. How about blue schist and green schist? Yes, Andy, there are different grades of all of these metamorphic rocks, and there are blue schists and green schists, which are different grades of schist. So you can see how you can get into the weeds here with this metamorphic stuff. You can be a full career metamorphic petrologist and do nothing but look at certain minerals that say you're in blue schist form or green schist form. And the point is, each of those kinds of schist that you're describing represent a particular temperature pressure condition. Generally, I don't know if that's too helpful for us here today. How would I classify slickensides? Slickensides are from fault action, where you have two fault blocks that are grinding past each other and you leave these kind of grooves in a fault plane itself. So unrelated to the metamorphic story tonight. Patrick, age 6. By the way, Patrick, I was doing the dishes last night and my mother called me by accident. It was 10 p.m. It was 11 p.m. in Wisconsin, 9 p.m. where I was. She said, "Oh, I didn't mean to call you, but I think you called Patrick by the wrong name after he asked a question." And I watched the replay, Patrick, and I did call you Daniel at some point. So I'm sorry. Did the garnets form first and then the rock around them was turned into schist? Those were big spaces for the minerals to grow into. Hello, Liz. That's an interesting thought, Patrick. I mean, Daniel. Just kidding. I'll have to ask somebody, Patrick. You're thinking maybe these garnets formed and then there was some sort of change and then you're kind of forming the schist around it? I'm sure we have a geologist who knows the answer. Maybe a geologist can chime in. I don't know. We can look at the boundary there. Maybe so. I see what your logic is there, Patrick. I like it. You want the answer? I don't know the answer. Good thinking, Patrick. AKA Daniel. Susan, is the Morrison Formation in Colorado metamorphic? No, it's sedimentary. I did my field camp in Park City, Utah, and I remember having to map the Morrison. Oh, Liz is watering the garden, which is the cue that I should be wrapping up here. Let's do 2 more, and then I promise I'll quit. Well, you guys are really into the garnets. I told you all I know about garnets. Are there sedimentary formations in Western Washington? Robert, we did one of these live streams called the Straight Creek Fault. This is how we'll finish. Once upon a time, there was a formation. And in geology, formations are a collection of rocks that tell a unique story. You know, somebody in the grocery store says, I love the rock formations when I drive in the canyon. And they're talking about the shapes of the canyon walls. But for us in geology, a formation with a capital F is a collection of rocks. So the Schwalk Formation is a collection of sandstones and shales that run from 59 to 49 million years old. And it was a low-lying swamp here in central Washington. Actually, all of Washington was a low-lying swamp with some occasional rivers draining from the northeast to the southwest. The remains, or the record of what those conditions were like during the Schwalk Formation, are the sandstones and shales, sedimentary rocks of the Schwalk Formation. And then something happened. A huge island called Silesia, a big old chocolate gumdrop out in the Pacific Ocean, slowly inched towards western Washington, and Silesia collided with Washington, where Seattle is located today. And that accretion of Silesia, the last exotic terrain to build Washington, formed a major strike-slip fault called the Straight Creek Fault. The Straight Creek Fault, a San Andreas fault-like structure that took our Schwalk Formation that dominated western and eastern Washington and broke it in half. And the western half of the Schwalk Formation got inched north with each big earthquake on the Straight Creek Fault, just like the San Andreas Fault behaves today. And today, the sedimentary rocks of western Washington, including the Chuckanut Sandstone near Bellingham, is the same exact sandstone as the Schwalk Sandstone and the Chumstick Sandstone of central Washington. The only difference is they've been offset by 100 miles. All of western Washington is 100 miles north of where it was 50 million years ago. You see, I couldn't hold it. I had to tell a story to finish this off. A toast to you. I won't see you tomorrow night, but I will see you Saturday morning at 9 a.m., Sunday morning at 9 a.m., talking about stuff that's not Rock Week. So we're at the end of our Rock Week program, and I hope that you enjoyed it. I got some work to do before this weekend. I suppose I'll figure that out tomorrow. Here's to you and your health. Here's to the health of your children, your grandchildren, your parents, grandparents, aunts and uncles, all of your extended family. I certainly hope, I genuinely hope that they are in good health during this pandemic. Thanks for joining us tonight. We'll see you Saturday morning talking about, I guess, the Milankovitch Cycles. Good Lord. We'll see you then. Goodbye. I love you.